Okay, Dimitri, are you ready? Can we start?
Yes, I'm ready.
Okay. So I will start recording now. Good morning, everybody. Welcome again to this new seminar from the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Dimitri Blinov from the Institute of Astrophysics, University of Crete in Greece. And he will talk about the RoboPol program, Optical Polarimetric Monitoring of Blazars. Dr. Dimitri Blinov obtained his PhD at the St. Petersburg University in 2012. Then he moved to the University of Crete in 2013 as a postdoc to work on optical polarimetry of AGN under a project called RoboPol, which he's going to talk about today. Ever since he stayed in Crete, in 2018, he joined the Institute of Astrophysics of the Foundation for Research and Technology, HELAS, as a researcher. Here, he is currently working on the largest ever survey of stellar polarization called PACIFY. So thank you very much, Dimitri, for accepting this invitation. This seminar was originally programmed to be given when you stay here at IAA in Granada, but then we move to this date, and thank you for accepting this, and the floor is yours, please.
Hello, everyone. Thank you, René, for the introduction, and thank you for giving me the opportunity to give this talk here. Why I made this talk now is because last year we finally made the public data release of the monitoring data of this project called RoboPol. So I think it's a good time to look back and see what has been done during these years and what kind of results we obtained. So I will talk about blazars. Blazars are a subclass of active galactic nuclei where we look almost along their relativistic jets. And for this reason, what we observe in the low energy emission from the radio to UV or sometimes even X-rays is the synchrotron emission of these jets that is strongly relativistically amplified. And aside from the synchrotron peak in the spectral energy distribution, there is also the secondary peaks somewhere between X-rays and very high energy gamma rays. And how this emission is produced is not so well understood. And it was even less understood something around 10, 12 years ago when NASA launched Fermi, which is a gamma ray space observatory. This image here on the bottom is the full sky map in gamma rays obtained by this Fermi Gamma Ray Observatory. And what we can see here is hundreds or thousands of sources. And 85% of these sources, point-like sources, are blazars. So when this observatory was launched, something around 2010, it started providing an immense amount of data for thousands of blazars. It was scanning the entire sky every 3 hours, so it was providing the very detailed light curves. But that time it was totally unclear where this gamma ray emission comes from in blazars. So there were very different models, and some of them I list here on the left part of the slide. Some of them were explaining that they were modeling this gamma ray emission by some processes happening in the very vicinity of a black hole, something like 0.1 parsec from a black hole. On the other hand, others were saying, no, this is a totally different process involved, something like tens of parsecs downstream of a jet. And all these models, they had good observational evidence proving their point. And around that time in 2010, there were these two papers published. What we emphasized in these papers is that, at least in some blazars, and sometimes there are this gamma ray activity, gamma ray flares, like this one's here or this one here, they are coincident in time and probably physically related to this kind of phenomenon of optical polarization plane rotations shown in this panel or in this panel here. So this phenomenon, I will call them optical polarization plane rotations or EVPA rotations. EVPA stands for the electric vector position angle. This is the events when the plane of oscillation of an electric vector in electromagnetic emission starts slowly moving towards one direction. And sometimes it can move for hundreds of degrees, like in this case, for example. So the first event of this kind was reported in this paper by Kikuchi in 1988. But since that paper till 2010, before these two papers, there was essentially no attention paid to this kind of phenomenon of optical polarization plane rotations. There were just very few examples of similar events detected in several blazars reported. But after these papers, it was understood, okay, if these events are indeed coincident in time with gamma ray flares, maybe we can learn something about these gamma ray flares. We can get some new clues just studying these optical polarization plane rotations. But unfortunately, it was very much unclear how these EVPA rotations are produced. So in this slide, I list 11 possibilities, 11 possible models and corresponding references. If you read these papers, you can right away understand that we're talking about very much different physical processes. So it probably tells us that we were pretty far from understanding how these EVPA rotations are produced in blazars. So this group of people whose names are listed in this slide, we decided, okay, let's look at these two poorly understood phenomena, the gamma ray flares and the optical polarization rotations together, and let's at least try to understand whether they are indeed connected and there is some common physics behind them. So we decided to establish this collaboration that is called RoboPol collaboration, with two main objectives in our mind is to observe a large statistically well-defined sample of blazars in linear optical polarization with a high cadence. And then we wanted to apply rigorous statistical methods to identify this kind of polarization plane rotations in this data and study statistically how they are related to gamma ray flares. And we were lucky enough to get time in this 1.3 meter telescope at the Skinekas Observatory, which is located in the middle of Crete. And the advantage of this site is, as in many other observatories located in islands, it has a very good and stable seeing. So we secured significant amount of time at this telescope, 4/7, for 3 years, or to be more precise, for 3 seasons, because we don't observe in winter. Then we built a special dedicated polarimeter that was made specifically for this telescope and specifically for this project. This polarimeter is also called RoboPol. And we made a relatively advanced control system and the pipeline for this instrument. So it was it automated significant part of the observation. For example, this control system is able to point to objects automatically. It's able to estimate their brightness on the fly and adjust the exposure needed to reach particular signal to noise. And it also processes data on the fly just some seconds after the observation and gives you the polarization parameters of the source you just observed. Then the main feature of this RoboPol polarimeter is this polarizing assembly made of 2 half-wave plates and 2 Wollaston prisms. And this set of elements, it splits every incident ray into 4 rays, as you see here, the projection of on the CCD. So each of these 4 rays have different polarization states. And measuring photons in couples of these rays and doing this simple math here, you immediately get the relative Stokes parameters Q and U. And then summing the counts in all 4 rays, you get the total intensity. And if you have some star with known magnitude in the field, you can calibrate the total intensity for your source, and you can translate the flux density in millijanskis, for example. So this polarizing assembly is stable. There are no moving parts, and that makes us makes our polarimeter very stable. It has very low level of systematics, and it's easy to operate. Okay, these are the main advantages of the polarimeter. Now, another important feature of our approach, of our monitoring program, was that we selected our monitoring sample based on the rigorous and strict statistical criteria. There are many other monitoring programs that observe blazars in the optical, but what we observed, we selected the most interesting, the most variable sources in gamma rays and observe only those. So if you ask those people from those monitoring programs, what is the average polarization of a gamma ray bright blazar, they cannot tell you because their sample are very much biased towards, very much biased with respect to the gamma ray properties of these sources, right? We had a totally different approach. We started from a complete sample of gamma ray loud blazars, and we applied a set of non-biasing criteria and ended up with our non-biased sample of gamma ray loud blazars. And we did the same for blazars that do not emit in gamma rays. We started from CGRAP sample that are blazars very similar to gamma ray emitting ones, with one exception. We were not registered by the Fermi-Lat that time. So we are going to apply non-biasing criteria, and we get our control sample of gamma ray blazars. On top of these two samples, we also added these hand-picked most interesting blazars, but we don't use them in our statistical analysis that I will report later. Okay. So after the first month of observation, we immediately got our first scientific result, and it is that gamma ray loud blazars are significantly more polarized in the optical band compared to their gamma ray quiet counterparts. So later, this result was confirmed using 2 years of monitoring data, where we averaged polarization for each blazar, and we found these numbers that on average, gamma ray loud blazar is 9% polarized and the gamma ray quiet is 3% polarized. And these two numbers, these two average values, are more than 4 sigma, are different at more than 4 sigma significance level. So this immediately tells us that gamma rays, they are somehow related to the optical polarization. So the interpretation we were proposing in these two papers that I cite here is that in gamma ray bright blazars, the magnetic field in the jet is somehow more coherent, more aligned compared to the gamma ray quiet ones, where it's more turbulent. So that's why we see the optical polarization that is higher, right? Then later we use this property, the high level of optical polarization of gamma ray sources, in this little side project that was published in this paper by Mandarakas et al. So what we have done, we demonstrated that optical polarization is a very efficient tool when you start searching for unidentified gamma ray sources. So the problem can be explained by this sky plot here. If you now take the latest Fermi-Lat catalog, which is called 4FGL, you see that there are 5,000 sources there, but you will also see that approximately a quarter of them are unidentified. So you know that the gamma rays, they come from somewhere here in the sky. These are the uncertainty ellipses. But even within the 3 sigma uncertainty ellipse, there are dozens or sometimes even hundreds of optical sources, and sometimes several radio sources. So you don't know which of these sources is responsible for the gamma rays, right? And it's not so trivial to establish this connection. But now we found that our blazars are so highly polarized, and especially those who emit gamma rays, they are even more polarized. Then what if we just measure optical polarization of all these stars within 3 sigma error ellipse? Then if these gamma rays are produced by some blazar here, this blazar should pop up in optical polarization, right? And we actually performed some simple Monte Carlo modeling using real data, using our data and reddening maps publicly available. We demonstrated that if for most of the sky, if you step out just 10-15 degrees from the polarization from the galactic plane, you are essentially always in this regime. So your interstellar polarization is less than 1%. And in this case, you should see blazars popping out among the field stars in polarization in something like 70 to 90% of cases. And what we have done, we actually went on the sky and measured 4 such unidentified Fermi sources. And in the field of one of them, we found this stellar-like source of 17.6 magnitude that was 5% polarized compared to the rest of the stars here that were less than 1% polarized. And then we measured the redshift of this source, and we found that it's indeed an extragalactic source. And we were also able to determine its class using the ratios of spectral lines. And it turned out to be a complex source made of an AGN and a star-forming galaxy around it, star-forming host galaxy. And probably that's why it has never been detected in any other surveys, because it had very peculiar colors that are not typical for AGN. And one more thing to say here is that when we published this paper, there was only 3 FGL, the previous version of the Fermi-Lat catalog available, and our source was somewhere between 2 and 3 sigma uncertainty ellipses, somewhere here. But then 1 year later, 4 FGL has been released, and we found that the gamma ray source moved towards our source in our favor. So now our candidate, now our AGN, is located within 1 sigma uncertainty ellipse of a gamma ray source. So we proved that optical polarization is really efficient when you start looking for unidentified gamma ray sources. But for now, let's return back to the main RoboPol monitoring program results. In this paper by Angelakis et al., we not only demonstrated that gamma ray faint and gamma ray bright blazars are very much different in optical polarization, but we also found these 2 dependencies that I think are interesting to discuss here. So on the left, what we see here is optical polarization, the average polarization for each blazar versus the synchrotron peak position of this blazar. So what we see here that the low synchrotron peak blazar sources, they have larger spread of possible polarization values, and they reach higher values of polarization compared to high synchrotron peak blazars that have very small values of polarization and small spread. Something similar happens also in the polarization position angle. So if we look at this quantity chi-square, that reflects how much the distribution of polarization plane direction deviates from a uniform distribution. We see this kind of trend that is noisy, but still there is a trend. We see that the low synchrotron peak blazars, they tend to have more uniform distribution of observed polarization plane directions compared to HSP sources, high synchrotron peak sources that tend to have a preferred direction of polarization plane fixed near some direction. And the interpretation of these 2 dependencies proposed in this model is depicted here. When we observe in a fixed optical band, as we do, we observe in the R band. When we look into low synchrotron peak blazars, we are somewhere here on the right-hand side of a synchrotron peak. And this emission is produced by highly energetic electrons that were presumably recently accelerated in the jet accelerated by some process, whatever it is, magnetic reconnection or some shock traveling in the jet. And this process presumably happens in a small fraction of the jet, and also it alters the magnetic field in the jet during this acceleration, right? So what we see is that this emission coming from this little region in the jet is highly variable. It's sometimes highly polarized, and it's also the magnetic field can be changing a lot due to this acceleration process. So we see very uniform distribution of polarization angles. On the other hand, when we observe high synchrotron peak blazars, we are somewhere here in this regime on the left-hand side from the peak of a synchrotron peak. And this emission comes from the population of electrons that already lost their energy. So these are presumably some electrons that traveled down the jet from the acceleration region and they probably feel larger volume in the jet. So all processes are already more calm, and there is not so much variability in the polarization. And we are probably dominated in this part of the jet by the large scale magnetic field of the jet. So that's why we see some preferred position angle in the polarization. Okay. Now, before I start discussing the results related to the EVPA rotations that we obtained, I need to make a couple of definitions and discuss a couple of caveats. So we always need to remember that any measurement of an electric vector position angle of a polarization plane direction is 180 degrees ambiguous. So this polarization plane is exactly the same as this polarization plane. We cannot distinguish these two cases. So whenever we have a set of EVPA measurements, this is not just one single EVPA curve, but an infinite family of EVPA curves, like shown here by these blue lines. And any of these curves is mathematically equivalent. So the only way to deal with this, to select one actual single curve, is to make your observations frequent enough so that the polarization plane does not have time to rotate more than 90 degrees between two measurements, right? So then what you do in practice, you check this condition, you check whether your current measurement deviates more than 90 degrees from the previous one. And if it does, you adjust it, you shift it by 180 degrees back or forth until you minimize this difference, right? But even this simple thing can be done in multiple different ways. For example, you can take into account this uncertainties term, or you can drop it. And there are different advantages and disadvantages of these methods of the solution of 180 degrees ambiguity. And this question is discussed in these papers that I cite here. But for now, I'm just saying that we were using in our works consistently this single definition that I'm showing here. But I cannot guarantee you that for whatever other possible way of a 180 degrees ambiguity solution, you can get exactly identical EVPA curves. It could be that with some other methods, you can get slightly different EVPA curves, okay? So this is my disclaimer here. And now, let's say you restore this single EVPA curve correctly. Now you need to define what is an EVPA rotation, when the polarization plane is rotating in this curve, right? And amazingly, if you look into papers before our project, there are EVPA rotations reported in those papers, but there is no definition what we consider an EVPA rotation. So we had to introduce our own definition, and this is shown here in text. But again, this is not the only possibility. There are various alternatives. You can define what you call an EVPA rotation different ways. And all results that I will refer in the next slides will be obtained for this kind of definition. Now, say you solved the 180 degrees ambiguity, you restored the EVPA curve, you defined where you have your optical polarization plane rotations, like the one shown here. You can, from this data now, you can derive three main parameters: is the amplitude of rotation in degrees, the duration of rotation in days, and you can define the middle point of rotation that we will use later. Now, what I was saying about rotations and possible definitions applies also to the gamma ray flares. There are several possible ways how to say what is a gamma ray flare or a flare in general in the total flux. We basically arbitrarily stick to this definition from this paper by Nalivaika 2013. But we also, again, arbitrarily replaced this factor by another one, by higher value, just in order to be sensitive to smaller amplitude flares. So this factor regulates the amplitude of flares that are considered as flares. So here I show an example. This is a photon flux curve for a blazar. And the red points are gamma ray flares according to this definition, right? And now when you defined where you have the gamma ray flares, you can fit them using, for example, this kind of function that gives to any flare an exponential rise and an exponential decay. And from here, from this fit, you can derive 4 main parameters, which is amplitude of flare, rise time, decay time, and the peak moment of a flare. Okay, and later I will use these quantities that I described in the slide. You will see them later. But now this is the slide illustrating our main result. So after 3 years of monitoring, we detected 40 EVPA rotations following the definition that I was describing before in 24 blazars that I will call rotators. So blazars who rotate polarization plane. And you see how it compares to the previous publications. So prior to RoboPol, there were 16 EVPA rotations in 10 sources reported in the literature. So as you see, we significantly increased the sample of known events. And here in the plots, the middle panel shows the EVPA, the polarization plane direction. And the red points are the optical polarization plane rotations according to our definition. So this is the minimal rotation for measurements with 3 significant swings between them, and the total amplitude is more than 90 degrees. This is another blazar. This is CTA 102. So there are 2 consecutive rotations in these blazars in the same direction within the same observing region. This is just to show you more or less to give a perception how they look, these rotations. Now, if you look into these numbers, you see that there are more rotations than sources. So these sources on average have more than 1 rotation. But on the other hand, you remember that our sample was containing something like 70 sources, 75 sources. So we have many more sources where there are no rotations detected. And now the first question that follows from this is, do all blazars exhibit EVPA rotations or not? So in order to address this, we consider these events of polarization plane rotations as a Poisson process. So there is some average frequency of these events, but each of them is independent from any other. So they just appear randomly, independently from each other. And then this kind of process follows the Poisson statistics. And then you can find the probability of having n events if you observe for the duration of time t, and the average frequency of events is lambda. So now we split our sample into subsamples depending on how many EVPA rotations was detected in each particular blazar. So we had, for example, 3 blazars where we detected 4 rotations along the 3 years of observations. And so we know all these numbers for each of these subsample. We know how long we were observing them. We can derive this average frequency. And now playing with these numbers from this table, putting them in this formula, we can estimate that it's very unlikely that all blazars show EVPA rotations with the same frequency. So this is the probability of this. So it turns out that there is a subset of blazars that exhibit rotations an order of magnitude more frequent compared to the other blazars where we didn't see rotations. And now the next question, what is so special about this kind of blazars, this kind of that we call rotators? It turns out that these blazars, they have larger amplitude of variability of EVPA even outside of EVPA rotation. So if you throw away these optical polarization plane rotations that we detected and just analyze the remaining part of EVPA curve, you still see that EVPA varies more and faster compared to blazars where we don't have such rotations. And also, these kind of sources, they are more luminous in gamma rays and they are more variable in gamma rays. And one more thing we found is that these rotations, they tend to happen in the low synchrotron peak blazars, as it's shown in this histogram. So this is distribution of sources in our sample by class, low, intermediate, and high synchrotron peak sources, and the distribution of rotations in the corresponding sources. You see that rotations tend to happen in LSP sources. And if you do some simple combinatoric exercise from a textbook, selecting, balls of different colors and estimating the probability of having a particular number of balls, exactly the same thing here, you can find that it is unlikely that this is just an accidental outcome. So there is like 1 or 2% probability of having this by chance, and 1 or 2 depends on what you consider as a parent sample. So we conclude from this exercise that rotations indeed tend to happen in blazars who have their synchrotron peak at the low frequencies. And again, we can remember here the model that we were discussing a couple of slides ago, that in this kind of blazars, in LSP blazars, we observe this very energetic population of electrons in a smaller region of a jet where some kind of acceleration occurs. So presumably optical polarization plane rotations are related to this kind of events. Okay, now what about the connection between rotations and gamma ray flares? Here I show several individual blazars, several individual observing seasons. The points are gamma ray photon fluxes. The red points are gamma ray flares, according to our definition. Then the green areas is where we have optical data, our observing season, as we call it. And the ticks, green ticks, is where we have individual optical measurements of optical polarization. And the pink region is where we had the optical polarization plane rotating. So after a quick glimpse at these plots, you see that most of these EVPA rotations were more or less intersect with some gamma ray flare, probably with one exception of this event here, where it doesn't, the rotation was not coincident with any flare, right? And now, actually, if you estimate the time lags between the middle point of the rotation and the peak of the closest gamma ray flare, you see that all these time lags are essentially consistent with zero, with just a couple of exceptions. So this is the relative amplitude of a gamma ray flare versus the time lag between the rotation and the gamma ray flare. And except these couple of points, this one and this one here, all other points are consistent within error bars with a zero time lag. But it doesn't tell that we are indeed related, because if you look, for example, into this gamma ray photon flux curve, you see that this blazar essentially always exhibits some kind of flare. So even if you randomly drop some rotation somewhere here, you will be always close to one or other gamma ray flare. So it could be that these time lags are so small just by accident. And in order to test this possibility, we made a simple Monte Carlo simulation, exactly like that. We were dropping random points in these green areas for each of these blazar and finding the closest gamma ray flare to this dropped random rotation, simulated rotation, and calculated the time lag between this rotation and the gamma ray flare, exactly the same as we did for the real data. And we repeated this 1 million times for the entire set of the events. And here in this plot, we show the distribution of these time lags as simulated. So the gray area is actually 1 million of CDFs, while the solid black line is the observed one. And what we find in this simulation is that out of 1 million of simulation, only 70 CDFs are located entirely to the left from the observed one. So only in 70 cases out of 1 million, the simulated time lags are smaller or equal to the observed one. So it gives us this small probability of having these time lags by accident. So we conclude from this simple simulation that at least some of these events, some of these rotations and gamma ray flares must be physically related. Otherwise, they would not be located so close in time. And if this is indeed the case, then we expect to see some correlation, some possible correlation between parameters of gamma ray flares and EVPA rotations. And this is exactly what we see in these two plots on the left-hand side. So on top, this is the amplitude of a gamma ray flare in units of luminosity versus the amplitude of EVPA rotation. And we see a negative correlation here. And the slope of a best fit line here is more than 3 sigma significant. So we conclude it's significant correlation. And something similar happens here when we compare durations of the two events. So vertical axis is the characteristic timescale of a gamma ray flare, and the horizontal axis is the duration of an EVPA rotation, of a corresponding EVPA rotation. And we again see some marginal correlation at the 2.8 sigma significance level here. Now we can remember that actually amplitudes of luminosities of gamma ray flares are related to the Doppler factors of blazars. And we again find that the Doppler factor of a blazar is related with the amplitude of EVPA rotations. You see this correlation here. And now also this Doppler factor is a function of a viewing angle of a jet and of a Lorentz factor of a jet, which is basically essentially the velocity of a jet. And in both cases, we find the significant correlation between these two parameters and the amplitudes of EVPA rotations. So from all these plots in this slide, it follows that gamma ray flares are indeed physically connected to the EVPA rotations. So this is the major finding of a RoboPol monitoring program. But now, since they are connected, we would like to know what is the actual physical mechanism, how they are connected. Unfortunately, it's not that easy to say because many different models explaining these EVPA rotations were able to reproduce the general properties of EVPA rotations as we observe them, the amplitudes, the durations, and even more tricky quantities like the one shown here. So we found this dependence in our observing data that during the rotations, on average, the optical polarization degree drops compared to non-rotating period. So you see the peak at something about 0.6. It's not trivial to understand why this happens. And actually many models, very different in physics, they see exactly the same behavior in their modeling results. So this is turbulent emission multi-zone model by Marsher. This is 3D full MHD simulation of a shock traveling in the jet. This is another model. It's a magnetic reconnection in the jet, and this is a simple random walk model. So they are very much different in physics involved, but they all have these rotation events, and they all during the rotation events we demonstrate the drop in polarization degree compared to nearby periods. Same here: rotation, a drop, rotation, a drop. So we cannot, it's really hard to discriminate which of this model takes actually place in nature. So we need some more sophisticated observables. And fortunately, we have them. So this plot on the left comes from this paper that I already mentioned in the introduction by Marsher et al. 2010. And what we have here is a set of gamma ray flares that are shown by these vertical blue lines that are coincident with optical flares. And if you calculate a ratio of a gamma ray flux to optical flux, this is so-called Compton dominance, you will see that there are two populations of flares here that have very different Compton dominance. So presumably it tells us that there are two different mechanisms producing these flares. Now, during this set of flares, there was also an EVPA rotation of record long amplitude, 720 degrees, two entire loops. And there was an ejection of a radio knot at the end of rotation. So this is the knot, it was quite prominent. So this is the LBI radio map, 43 gigahertz. And all this set of events was explained by a model in this paper that is sketched here on top. So what we have here is a fast spine of a jet permitted by a helical magnetic field. And there is a moving emission feature propagating in this spine. Since it traces different parts of the jet where the magnetic field is oriented in a different way, we see the EVPA rotation during its propagation in the jet. And then this spine of a jet is surrounded by ring-like condensations that are moving with much slower speed. So there is some kind of sheath made of separate rings. And every time when this emission feature passes through each of this ring, it it encounters an external photon field made of this ring, which is highly boosted in the reference frame of a moving emission feature, and it upscatters these photons to gamma ray energies. So every time this emission feature passes through this kind of ring, we see an external compound gamma ray flare. And then this emission feature reaches the standing conical shock at the end of a collimation acceleration zone that we presumably see as the radio core and VLBI radio maps. So at this moment, it compresses the magnetic field, so it becomes very much aligned the magnetic field. And at this moment, we see very high level of optical polarization. We see a synchrotron flare and a synchrotron self-Compton flare. And also at this moment, the emission feature passes through the radio core. So we see the new knot appearing at this moment at the radio maps. So interestingly, aside from this explanation, there was a very clear prediction made in this paper, is that if this system of rings in the sheath of a jet is persistent enough, then the next emission feature propagating in the jet another time will also follow the same path, more or less, and will also pass through the same set of rings in the sheath of the jet and will produce the corresponding set of gamma ray flares, external compound gamma ray flares, coincident with an EVPA rotation or close to it. Okay, so very clear prediction, and we were thrilled to test it. We collected all the EVPA rotations, all blazars with more than one EVPA rotation in the literature and in the RoboPol data. And we found this source. This is 3C279. What we have here is a gamma ray photon flux top, then optical magnitudes, optical polarization degree, and the EVPA, electric vector position angle. What we have here is three large EVPA rotations. They are emphasized by these pink regions, 1, 2, and 3. And now if we take the pieces of a gamma ray curve between vertical dashed line, here 1, 2, and 3. So as you see, they are either very close or coincident with EVPA rotations. And now we stretch this region 2 by this factor and squeeze region 3 by this factor. We see that they become very much similar. And this is not just a visual similarity. Actually, in the paper, we demonstrate that it's we mathematically demonstrate that this is the best fit pieces of a gamma ray curve in the entire observing period under these stretching and squeezing factors. So we believe this is exactly what was predicted by Marshall et al. 2010. We have a set of repeated gamma ray flares, repeated pattern of gamma ray flares that happens next to large optical polarization plane rotations. And the squeezing and stretching here is needed because the emission features, they move in the jet with different velocity. So they pass the same set of rings with different speed in our rest frame, right? Now I see I'm a bit out of time, so I will shortly say that we also found a hidden EVPA rotation that you don't see in the EVPA curve, just because there is an underlying highly polarized source that shifts all your points in the QU plane. So whenever there is a loop on the QU plane, you cannot see it in the EVPA curve, but you can detect it as a loop here. So we detected this set of points that is 3/4 of a loop. And if you would shift all these points, the centroid of this distribution to the 0, 0, and all points accordingly, you would see 120 degrees EVPA rotation in this interval of time in between two green vertical lines. And again, if we take this light curve for the same time range and stretch it by this factor, we again see a similar pattern. And we believe that this is the fourth repetition of a gamma ray flares pattern that this time happened during the hidden EVPA rotation. Now, I will briefly say that we, as in Marshall et al. 2010, we also had ejections of new radio nodes after all our events. For this first event, we have two possible candidates. Uncertainties are large here, so we don't know which one was responsible for it. In the event number 2, we don't have an ejection of a radio node, but as you see, there were no ejections for a long time here. This is because the two previously ejected nodes, C32 and C31, were extremely bright. They were brighter than the core itself, like shown in these plots. So we were presumably outshining everything. So we could not see new nodes ejected during this period of time. That's why we don't see any ejection. And also using parameters of these radio nodes, we estimate the size of the emission zone responsible for this repeated pattern of gamma ray flares. And we find that it's 11 parsecs in size. So this could be only the sheaf around the jet, nothing else, because all the other possibilities were much smaller in size. And this is the model summarizing a few previous slides. So we have this spine of a jet where the emission feature travels with different velocities. Several of them are ejected. And every time it passes through a set of rings, next to each ring, it produces a gamma ray flare. And we see this repeated pattern 3 times with different time scale, depending on how fast the emission feature in the jet it was traveling. So we are pretty much confident that this mechanism actually works in this particular blazar, and this is how the EVPA rotations are produced in these blazars, and this is how they are related to gamma ray flares. But on the other hand, we cannot guarantee you that in all other blazars, this is the only mechanism producing EVPA rotations. For instance, we know that there are much faster EVPA rotations that occur, that rate of those EVPA rotations is sometimes hundreds of degrees per day. And this model is not suitable to explain those kind of events. But they are also very hard to detect because you need to observe a very high cadence and very much uninvestigated. So probably there is some other mechanism also working here that can also produce EVPA rotations. So I will skip a few slides. I will just tell you that we are now working on a different project that is unrelated to AGN, and we are essentially building 2 other polarimeters that we can say will be RoboPols on steroids. So we employ the same idea. Each ray is split it into 4 rays with different polarization state. But this time, each of these 4 rays will be projected on a separate CCD. And we will have a large field of view. So we will have a ½ degree field of view. And the point of this project is to observe a large fraction of sky at high galactic latitudes from both hemispheres. We will have two sides, 2 polarimeters and 2 telescopes. And the idea is that we will be able to observe millions of stars in optical polarization, and thereby we will perform a 3D tomography of a magnetic field in our galaxy, and we will be able to subtract the foregrounds introduced by our galaxy from the microwave emission, so that we will help the CMB projects that are looking for the B mode in polarization of the CMB. Yeah, so this is an ongoing project, and now we're building these polarimeters. So stay tuned and follow our webpage if you're interested in this kind of science. But now I reached my conclusions. And the main conclusion of RoboPol is that optical polarization plane rotations in blazars are indeed physically connected to gamma ray flares. And the model that I demonstrated to you is probably responsible for a significant part of these kind of events. So thank you for your attention. Feel free to use our data that you can find in this paper that I'm showing here. Thank you.
Thank you very much, Dmitry. Wonderful talk. And now the talk is open for questions. Please raise your hand for doing the question, and I will let you ask Dmitry. Questions? We have one. Ivan, please go on.
Hello, Dmitry. Thank you very much for your nice talk.
Ivan.
It was very nice. I have one question about the model that you have outlined for the work on 3C279 that you showed a few slides before, which is, I understand it's based on the one by Alan Marshall in the paper about 1510 on 2010.
Yeah, exactly.
So it's essentially about the rings that are producing the external the external seed of optical photons for producing later the synchrotron, the inverse quantum flares in the gamma rays. What is the idea that you have for those rings? I mean, you know, relativistic jets are dynamic systems, so maintaining those rings there perhaps implies a very particular set of conditions to keep them on time, so that the same kind of phenomenology is observed in separate times. So what is the idea, the origin essentially of the?
Yeah, that's a good question. I think nowadays in the literature, it is discussed several possibilities. It could be related to the way of accretion goes. So it could be some sort of property of the accretion disk and the accretion process that produces these rings. Or on the other hand, there are some other possibilities. So we do not discuss this in our paper. We just say, okay, this is the pattern of flares. This is the only way how to explain that it exists. They seem to be very persistent because this first repetition of a pattern is separated from the last one by 6 years in our observer's frame, right? So they seem to be persistent along this pretty long time, but we do not discuss how they could be so persistent and why do they exist and how they're produced. We just say we found that they exist and that's it. And I think it's a long discussion. There is no simple answer to this question. There are several possibilities, and again, it's unclear which one of them is correct.
Okay.
So I'm not ready to answer to this now.
All right, yeah. Am I allowed to make another question? Yeah, this is more on the technical side regarding. I mean, I would like to know what is the precision that you get on the optical polarization measurements that you do on standard Blazars, let's say, you know, magnitude 15 in error band or something like that, and essentially how much improvement you have with an instrument like the RoboPol polarimeter as compared to the most simple version of our polarimeter, which is a simple filter wheel with different angles for the polarizers.
Yeah, so I think in a sense we had an overkill with this polarimeter because it's indeed too accurate for Blazars, let's say. As you have seen from some of those plots, Blazars are sometimes like 10% polarized, 20, 30% polarized. And you don't care much about accuracy, right? Even 0.5% accuracy will be totally enough. You will still have 15, SNR 15, right? Here we have accuracy something like 0.1%, and even better. If you are really careful, you can reach accuracy 0.1%. And it's not really needed. You indeed can reach accuracy 0.5 with much simpler, much cheaper polarimeters, like the one you said, or even with two simplest Savar plates installed in a filter wheel under 45 degrees rotation. And it's totally sufficient for Blazars. But we are also performing different type of science with this RoboPol that needs higher accuracy. For example, interstellar medium studies. The higher the accuracy, the better it is. So I don't know if it replies to your question. So shortly saying, you don't need so accurate polarimeter for Blazars, but if you study something else, it's profitable.
Okay, yeah, good answer. Thank you very much.
Thank you, Van. Another question for Dimitri? Okay, seeing none, I will thank you again, Dimitri, for this talk, and thank you everybody for being here.